Hello again, AP class. We are almost done with probability. So today, if you look at my title, Probability, the End. This is the last of all of the random probability stuff. Okay, so a quick couple vocabulary words here. Union. When you see people mention union, it's going to look like A, then they'll put a little U in there, and then B. That little U, that is the union symbol. And it's the set of all outcomes in A and B or in both A and B. So it's kind of getting everything included in there. The intersection is the A, then they do the upside down U, then B. That's the intersection. It's the set of all outcomes that are in both A and B, but not in outcomes A and B, A alone or B alone. So the union kind of includes everything. The intersection is just where the two kind of overlap is the idea. Okay, so just to kind of clear up, if you're using different textbooks, they do use the union and intersection symbol, which is why we like to point those out. Now, we're also going to revisit tree diagrams. Okay, this is obviously a much more complicated problem. You can just tell by the size of the paragraph. Then, let's set up and make a sample space. That's what we use tree diagrams for before. Well, here you've got this big scenario. Online chat rooms are dominated by the young. Teens are the biggest users. If we look only at the adult internet users, those are people 18 and older, 47% of the 18 to 29 age group chat, as do 21% of those age 30 to 49, and just 7% of those 50 and older. To learn what percent of all internet users participate in chat rooms, we also need the age breakdown of users. Here it is. 29% are aged 18 to 29, another 47% are aged 30 to 49, the remaining 24% are 50 and over. What is the probability that a randomly chosen user of the internet participates in chat rooms? Well, you've got kind of different things happening here. You have people who are users, you have people who use the internet but chat. Some people use the internet and don't chat. So what I'm going to do here is I'm going to focus first on the age groups. Okay, we have three of them. We have the 18 to 29, the 30 to 49, and the 50 and older. So this is kind of my first kind of division. And in there, you do have different probabilities. We have 29% are in this first group, so I'm going to put 0.29 on this line. 47%, 0.47 goes to the 30 and 49. The remaining 24% are going into the 50 and older. Now, that's just our three age groups. In each age group, some people chat and some people don't. Well, so I'm going to break these two apart. I'm going to say, let's say user or not. And I'm going to do that for all of these. User or not. And we have user or not. Okay, so now we have to look at each individual age group. Okay, 47% of the 18 to 29 chat. So that would be a user. So 0.47 again. The not, well, that's everyone else. If you do 1 minus 0.47, you get 0.53. Okay, and that little kind of branch is done. 21% of those in the 30 to 49 are users. So 0.21. 1 minus that. On the flip side, we've got 0.79 who are not users. And then just 7% of the 50 and older, so 0.07, which means 0.93 are not chatting online. So it does kind of look like a tree diagram, but we have these probabilities that are flowing down it. They want to know what is the probability that a user chosen at random participates in the chat rooms. So if I had to kind of follow down my lines here, well, I'd have to go through an age, and then yes, they use. age they use, age they use. Like my highlighter? It's nice, isn't it? So if I'm going to go in here and actually find my probability of users, what I'm going to have to do is actually multiply down. That first row, we've got the 0.29 meets 0.47. So 0.29 times 0.47 plus, do the next age group. 47 flows into 0.21. So 0.47 times 0.21 plus, go down that third branch, we have 0.24 times 0.07. And if you simplify all of that, I get 0.2518. That is the answer to this massive story problem. So the flow chart, you got to set it up, but it's the probabilities within it that we're going to use for this problem. That is only really when we have lots of categories, lots of percents. If there's a lot of different kind of parts happening, this is what you're going to do to solve. All right, we have another magic word for you. It's a new phrase. If you ever see them mention the phrase at least, there is a trick. We're going to change that phrase into 1 minus none. Okay, so magic word at least, change it to 1 minus none. And how this is going to work, I'll kind of start simple and kind of build you up here. In a box of 11 parts, 4 of the parts are defective, 2 parts are selected at random without replacement. In part A, they want us to find the probability that both parts are defective. Well, 4 are defective. If 4 are defective and you have a total of 11, that means the other 7 are good. Okay, so that's kind of worth noting. Okay, if part A wants us to find both are defective, there are 4 defective pieces out of 11, and I take a defective one out. I go in for another one, there are 3 remaining out of 10. I know that is because without replacement. And that gives me a probability of 0.109. Part B, find the probability that both parts are not defective, meaning they're going to be good. All right, AKA both good. Okay, well, there are 7 good ones out of 11. I pick a good one out. I'm going to go in for another one. So I'm at a 6 out of 10. That is going to give me 0.382. Now, here's our new phrase. Find the probability that at least one part is defective. Now, it's all about changing the wording. We want the probability at least one is defective. Okay, well, at least one, we're going to change it into 1 minus none of them are defective. I'm going to throw that extra detail down there. If none of them are defective, then that means they are all good, which we just found in part B. So 1 minus, let's reuse that 0.382, and that gives me a probability of 0.618. Okay. That is how you change the wording to make the at least problems work. Okay. 1 minus none.